Okay, can you guys see my slide?
Can, sir.
Okay. Oh, before I forget, please join the Google Classroom link that I've shared with Rania. Okay, so that is where I will post all of the materials, for example, like today's recording, all the slide, and any other extra materials. Okay, and if there are any tutorial also, you have to upload at the Google Classroom like previously. Okay, so all right. Uh, okay, unit one, uh, theory of resonance. So this topic is not that long. Okay, it's not that heavy. So previously you have encountered the terms resonance. Okay, it is basically it tells you about movement of electron through a pi bonds. So if you see any compound that contain a double bond, which is a pi bond, that means the compounds have a tendency to form resonance structures. Okay, the learning outcome. Okay, you should understand basic concept of resonance, stabilization of allyl ion or allyl ion and conjugated diet and so on. So what is resonance? So these are the definition or terms that you have to know. Okay, resonance is the use of two or more Lewis structures to represent a particular molecules. So if you still remember what is a Lewis structures, Lewis structures is basically a simplified version of a compound to show the valence shell electron. Okay, so we use this type of Lewis structures to represent a molecules, and the resonance structures is a way to describe how the localized electrons are located within certain molecules or polyatomic ions, where bonding cannot be expressed by a single Lewis structures, in which that they have multiple shape. So for example, if you look at uh, the if you look at the first structure over here, so for example, let's say that this compound is undergoing a reaction, and the electrons between this carbon and this bromine are being taken by this bromine, so in which that this bromine will become Br negative, so bromide ion. So this carbon over here will become positive. So this is the intermediate. So these are the intermediate form or a carbocation ion. But over here we have this C double bond C, which is the pi electron. So this allows electrons to move. Okay, electrons to move, which results in resonance. So that is the resonance. So how does it affect the structures? In which that electrons from here, okay, electrons from this double bond, it will be from this carbon, it will be shifted towards this C plus. Okay, now the double bond is bonded between this carbon and this carbon over here, and the positive signs is shifted from carbon this position to this position. Okay, actually the movement of the arrow should be from this double bond to this carbocation ion, because only electrons can move. Okay, not the positive sign. The positive charge cannot move. Only electrons can move. So it should be from here to this. Hence, it form a double bond, and this carbon, this original carbon will become positive. So it's like this middle carbon. First, it shared its electron with this carbon, but now it wants to share the electrons with this carbon. So it form a double bond over here, and this side will become positive. So these two are the resonance structures of the intermediate, okay, of the intermediate. And another example is whereby you have C double bond O. The pi bond is between carbon and oxygen. The first example is between carbon and carbon. So let's say the hydrogen is being taken out, okay, by a nucleophile, for example. So a nucleophile comes and take the hydrogen to form this intermediate. So in which that this oxygen will become negative. Why negative? Because the electrons that it previously shared with this hydrogen is being given back to the oxygen. So O become negative. So this is the intermediate. But now this negatively charged oxygen, it has one extra electrons that it want to share with this carbon. Okay, carbon must always have 4 bonds. Okay, it shared with this carbon. So what happened to this extra electron? It will be given to this oxygen. So now the negative signs is shifted from this oxygen to this oxygen. Okay, so these two are the resonance structures of this intermediate. And the resonance structure is not restricted to only 2. Okay, so it can be more than that. Some compound may have 3, some compound may have 4, and most of the time it is what you call that, determined by the number of double bonds present in the compound. If you have a lot of double bonds present in the compound, most probably that the resonance structures will be more than 2. Okay. So then another concept or term that you should know is the conjugated systems. So this one, I believe you have encountered in what do you call that, addition reaction in chapter 6, electrophilic addition reactions. Okay, you have found, if you still remember on the topic of diene, you have conjugated dienes, non-conjugated dienes. So a conjugated systems or conjugated dienes is when you have a species that have p orbital on an atom adjacent to a double bond. So what does it mean by is that you have a conjugated system, you have a double bond, single bond, and double bond. So that is what it is. So, but here you have to know another new terms. Is what you call as an ALL, ALLYL. So the general formula for an ALL is CH2, okay, CH2 double bond CH, CH2R. Okay, so you ignore this first, R over here. So that is a general formula for an ALL. So ALL can be a radical, ALL radical. So radical is it contain 1 electrons. So this is neutral. Okay, and it can also be an ALL cation. So in which this carbon is positively charged. This carbon contain 1 unpaired electron. So this is a radical. This is a positively charged carbon. So ALL radical, ALL cation, and this is a diene. And in fact, this is a conjugated diene. So you have C double bond CH, CH, then double bond CH2. Okay, so conjugated radicals, ions, or molecules are more stable than non-conjugated one. So these radicals are considered to be conjugated. Why? Because it has double bond and then single bond. Same as well as this one, ions, double bond, and single bonds. So this statement over here, conjugated radicals, ion, or molecules are more stable than non-conjugated ones. So this will be your tutorial questions. So find out and then answer them and submit on Google Classroom. So throughout the lecture today, so I will highlight some parts in the slide in which that you have to find out the answer. Okay. So later I will share the slide in Google Classroom as well. So allyl or allylic substitution and the allyl radical. So to show the resonance theory throughout this unit, we will be using allyl as an example. Okay, but at the end of the part, there will be die-in as well. So here we have a addition reaction, and the one below is free radical substitution. So at low temperature, it is said that here you have propene, both reactions have propene, but at low temperature, when it is react with a halogen, okay, either bromine or chlorine, the usual addition of halogen to the double bond takes place. So this is the electrophilic addition reaction. Okay, is what we have learned in chapter 6. Okay, so for example here, let's say you have Br, so the bromine will be added to these two carbon. So this is addition reaction. But at high temperature, or the concentration of the halogen is very small, substitution reaction will occur. So instead of the bromine is being added to these two carbon, substitution reaction occurs, in which that only one bromine will be substituting one of the hydrogen at the carbon, okay, and the double bonds between these two carbon will be retained. Okay, so this is what you have learned in chapter 7 or unit 7, which is free radical reactions. So the relative stability of the allyl radical. Later why so here you have delta H. Delta H meaning the energy level. Okay, lower energy level means that the structure of the compound is more stable. Okay, more stable. Here you have allyl radical. This is a tertiary radical, carbon radical, secondary carbon radical, and primary carbon radical. And the last one is vinyl radical. Vinyl, the structures of vinyl is CH2 double bond CH, R. So it can be a cation, it can be an anion, okay, but it comes from this starting material, okay, which is actually ethene, okay. So this is also the starting material for what? PVC, polyvinyl chloride. So in polyvinyl chloride, this hydrogen, these two hydrogen is being replaced with chlorine. So hence the word vinyl. Okay. In terms of this stability, as you can see, the delta H here is 360, and then it slowly increase, okay, based on this trend. So it shows that when you have an allyl radical, it makes the whole structures more stable. So what are the difference between this allyl radical and also these three? Okay, these three does not contain any double bond. So this double bond over here, it helps to form resonance structures to stabilize this whole intermediate form. Unlike this one, okay, doesn't have double bond, doesn't have double bond, doesn't have double bond. But for this vinyl radical, it also contains double bonds. But why does it become the least stable? Okay, why does it become the least stable? So find out this as well. Why does vinyl radical is the least stable in terms of relative stability? I already told you in this allyl radical, it contains double bond. Okay, double bond, it helps to form resonance structures. This one cannot have resonance structures, cannot have, and this one also cannot. But this vinyl radical, it contains double bond, but it is the least stable. Why is that? Sedangkan earlier, all that contain double bond should have resonance form, right? It should be more stable. But why does this vinyl radical is the least stable? So please find out on this as well. Later I will highlight in yellow on the slide that I share. Okay. So resonance description of the ALA radical. So originally, let's say this is the structures of the ALA radical as A. So this is the A. But it also has the same equivalent structures. This one B. More or less, this looks like a mirror image. Okay, we can say that it is the same, but in reality, the position of the electrons are totally different. Okay, because let's say you start this as carbon number 1. Okay, now the radicals are at from the third carbon to the first carbon. So what actually happened in terms of electron movement is, you see that these two electrons are actually comes from the pi bond. Okay, the double bond that is being shared. The one straight line is the sigma bond. Okay, sigma bond is very hard to break, but pi bond is easier. Okay, easier to be broken. So now at first carbon number 1 and carbon 2 shared the electron, but now carbon number 2 wants to share that electron with carbon number 3. So it takes this electron and move it here. And this radical, the electron here, will be shared also with this carbon number 2 so that it form a new pi bond. Okay, pi bond. And the original electron that is shared between carbon number 1 and carbon number 2 will be now act as a radical, okay, as an unpaired electron over here. So structure C over here blends the features of both resonance structures. So it's like dotted line, meaning that it's partially bonded, okay, half. So they are sharing half of electron. So these are molecular orbital description of the ALA radical. So don't worry too much about this because you have not learned on the basic of MO. So, but I just want to show you how the electrons is actually is. So here we have ALA cation, ALA radical, and ALA anion, and how much of pi electrons it contain. Okay. This one contain 2 pi electrons. The radicals contain 3 pi electrons. So molecular orbital is used to explain how the electrons are interrelated with energy level diagram. Okay. Actually, if you want to know in greater detail, you have to go back to it's part of general chemistry topic in which that you have to learn from beginning, but it's not covered in your syllabus, so don't worry too much about this. So I just want to share how the what you call that electrons are being relates with the energy level. So you have 3 isolated p orbitals. So what does it mean is this is at this carbon, this one is at this carbon, this one is at this carbon. So what happened is these 3 pi electrons that is available on these 3 carbons, 2 of them will go to the bonding level, and 1 will go to the unbonding one. Okay, which is the non-bonding MO will be this radical. Okay, 2 of that is already bonded. Where? Between these 2 carbon. Okay, these 2 carbon. This carbon contain 1 electron, this carbon contain 1 electron, and they are bonded with each other. So hence bonding. While non-bonding is this one. Okay, in which that the unpaired electron exists as a free radical over here. Next, we go to the allyl cation. Okay, before I go into this, any question on the last part? Ada? Can I proceed? Ada. If not, then I'll just continue. So, in terms of allyl cations, now instead of having an unpaired electron on this carbon, one unpaired electron, you have this carbon actually contains a positive charge. Okay, that means it lacks an electron. Okay, it lacks an electron. So allyl cation is more stable than a secondary carbocation and almost as stable as a tertiary carbocation. So if you look at this, okay, this is the allyl. It is actually not the most stable form. A tertiary carbocation is more stable compared to the allyl, unless you have a substituted allylic. That means on this carbon over here, instead of having two hydrogen, one of them is a substituent. For example, this carbon. Okay, this carbon with extra chain. Okay, so a substituted allylic will be more stable compared to a tertiary than only your allyl carbocation, and then you have your secondary carbocation, primary, and the least stable will be a vinylic carbocation. So the movement of electrons in terms of allyl cation. So basically, unlike the free radicals, electrons from what you call that, two carbons move. Carbon number 3 also will be sharing with carbon number 2 just now, right? But now in carbocation, since this, since the third carbon over here does not contain an electron, in fact, it is positively charged, so there are no electron movement. The electron movement only happen from the electron between these two carbons. So what happened is the electrons from carbon number 2 that is shared with carbon number 1 will be shifted here. It will be moved here so that now it is sharing with carbon number 3. So what happened to carbon number 1? Now it lacks one electron, so hence it becomes positively charged. Okay, so these two are resonance structures. So D and E are equivalent resonance structures. These allyl cation are unusually stable, so very stable. So positive charge located on C3 in D, okay, and on C1 in E should be delocalized over both carbon. And this is the hybrid structure. And this is the molecular, what do you call that, orbital, molecular orbital description of the allyl cation. Okay, what happened just now that I showed you, that it only contains 2 pi electrons. Okay, 2 pi electrons, and both of them are bonded. Okay, bonded. So there are no non-bonding. So unlike a radical just now, you have one non-bonding pi electron on this carbon. So you have one here, but now only two pi electrons. So both of them are being used in this pi bond, so bonding. So estimating the relative stability of resonance structures. So how do you know which resonance structures is more stable than the other. So first thing that you have to look into is the more covalent bonds a structure has, okay, the more stable it is. Let's say between what do you call that, resonance structures of resonance structure number 1 and resonance structure number 2 or resonance structure number 3. So between these three, let's say the second structure has more covalent bond instead of number 1, number 3. So that means the resonance structures number 2 will be more stable. Okay, covalent is sigma bond. Okay, if you already forget what is covalent bond, it's basically a sigma bond. So structures in which all of the atoms have a complete valence shell of electrons are specially stable and make large contribution to the hybrids. So complete valence shell electrons, that means the outer shell of let's say carbon, it contain 4 bonds. Okay, it completes, or probably if it doesn't contain 4 bonds, the carbons has 3 bonds and also 2 electrons. So that means it is still the octet rule are being fulfilled. And the third one, charge separation decreases stability. So I want to find out what does it mean by charge separation. So it basically it relates with how the electrons are being distributed throughout the structures. So that is the general idea. So find out what is this charge separation means. So these are alkadiene, or basically a diene. So you have 3 types. Okay, I think you have encountered this before. You have a conjugated dienes in which you have double, single, and double. Cumulated dienes, which is side by side. You have double bond and double bond. And also isolated. Isolated, that means the position of these 2 double bonds are quite far from each other. For example, let's say it is being separated by 2, 3 carbons, okay? So it does not affect one another. So let's take a look of conjugated diene. So we are focusing on these conjugated dienes, okay? So that so unlike this and this one, since it is not side by side, basically like for example this one is not side by side, basically the chances of having resonance are quite low, as well as this one, since it is already side by side. So electron cannot move here, electron cannot move here. Same like this one. If electrons want to move from here to here, it is very far. It has to jump 2 carbons. Electrons can only move only once, okay? It's like it can only jump from 1 carbon to another carbon, to the next carbon. Okay, it cannot go from here to here, okay? So in terms of stability of these conjugated dienes, okay, so normally conjugated dienes will be more stable than non-conjugated ones. Okay, example, here you have normal alkane, which is the more stable, okay, since it doesn't have any pi bond whatsoever. So the CC bond are very strong. It has the lowest energy level. But when you compare between conjugated diene, and this is a just a normal alkene. So this conjugated diene is having lower energy level. So lower energy level meaning lower delta H. It has more stability compared to this one. So along with resonance, so here electron can move to this middle carbon. Okay, hybridization energy affect the stability of the compound. So extra stability of the conjugated dienes comes from the stronger central bond that they contain. Which central bond? this one, C bond. This is sigma bond, okay, which is strong. And in part from the additional delocalization of the pi electrons that occurs in conjugated diene. So these pi electrons can freely move to the next carbon, okay, so that it will be forming resonance structures. So now we take a look at how this affect the electrophilic attack on conjugated diene. So basically this is addition reaction. In chapter 6, last time we have touched a little bit on this. So example, here we have 1,3-butadiene. 1,3-butadiene reacts with one molar equivalent of HCl to produce two products. Okay, here, over here, the chlorine is added at this carbon, okay, and the hydrogen at these carbons. Hence, you have these structures. Or you also have this, the second one. Okay, so how does the double bond from at the end suddenly be in the middle? Okay, so later we'll see how this second product is formed. So there are two types of addition. Okay, the first one is known as 1,2 addition, in which that the hydrogen is being added to carbon number 1 and chlorine at carbon number 2. And we also have this 1,4 addition, in which that the hydrogen is added to carbon number 1 and chlorine is added to carbon number 4, the last one. And the double bond is being shifted from the third and fourth carbon to second and third. So the mechanism of the addition reaction, basically, it involves this intermediate of allyl. Okay, this is what in the previous slide, okay, the allylic cation. So basically, once you have electrophile here coming in, so this electron from the double bond will tend to take this hydrogen. So now one of the carbon over here will be having this hydrogen. So based on the normal rule, hydrogen will go to the carbon that has more hydrogen. So it will go to this one, CH2. This one has only one hydrogen, so it will go to the CH2. So now it forms a carbocation intermediate, in which the structure is CH3, C plus H, and then CH and double bond CH2. So this can form resonance form, in which that this electron over here now wants to share, okay, this electron from this carbon. Originally, it shares with the last carbon, carbon number 4. But now it wants to share with the second carbon. So the electron movement from here to here. Okay. Wait, okay, the electron move from here to here. Okay. So now this carbon is no longer positively charged. Okay, because it already contains C double bond C. So what happened to this one? Now it lacks one electron. So once it lacks one electron, it will be positively charged. Okay, it will be positively charged. So hence you have these two resonance intermediate structures. Hence you will get two products. So this chlorine can either go to this carbon or it can go to this carbon. So you will have 1,2 addition and also 1,4 addition. So addition to one of the inner carbon, atoms would have produced a much less stable primary carbocation, one that could not be stabilized by resonance. So this hydrogen, okay, this hydrogen cannot be added to this carbon, okay, to form this one, because the carbocation form will be primary, okay, primary. So no reaction happen, okay. Instead, this hydrogen will always go to this one, so that the carbocation form will be secondary like this, okay, secondary. So 1,3-butadiene shows 1,4 addition reaction with electrophilic reagents other than HCl. So for example, if you are using HBr, then the major product form will be 1,4. Okay, 1,4 addition. Okay, hydrogen is added here, and bromine is added at the last carbon. Okay, and but if you lower the temperature, the amount is almost what you call that, equal, okay, between 1,2 addition and also 1,4 addition. Next, we'll see what is the effect of temperature on 1,2 and 1,4 additions. So the amounts of these two products can be affected by temperatures, okay, high temperature or low temperature. So let's say if you have this 1,3-butadiene, okay, 1,3, position number 1, position number 3, butadiene, 2 double bond, and HBr react at low temperature, which is negative 80 degrees Celsius, in the absence of peroxide. The major reaction or major product form will be the 1,2 addition, which is this one. Okay, 1 and also 2. Carbon number 2 and carbon number 1. H kat sini and also Br over here. But if you increase the temperature to about 40 degrees Celsius, okay, then you can change the major product to become 1,4, okay, instead of 1,2. Even in fact, if you increase the temperature to the mixture form, okay, let's say once you have this product and then you increase the temperature, the new reaction mixture will eventually contains the same proportion of products given by the reaction carried out by the higher temperature. So at higher temperature and in the presence of HBr, 1,2 adduct is basically products, rearranges to 1,4 product, and that an equilibrium exists between them. So you have this equilibrium, okay? And the equilibrium favors the 1,4 addition product. 1,4 adduct must be more stable. So find out why 1,4 adduct, why this is more stable than this one, okay? You have learned this. Why this structures is more stable than this. Okay, and here, as you can see, the arrow is pointing towards, the bigger arrow is pointing toward the 1,4 addition. That means that the reaction favors the right side product. Okay, if you still remember your equilibrium, chemical equilibrium in pharmaceutical chemistry 1 or in general chemistry, so bigger arrow to the right. So that means the reaction shifted towards the right. So this part is more stable than the starting material itself. This one. Okay, and to the last part, which is the Diels-Alder reaction. So this reaction was actually created or founded by these two researchers, okay, Otto Paul Hermann Diels and also Kurt Elder, which they are being awarded Nobel Prize in Chemistry in 1950 for finding out about this reaction. This one also you have learned a little bit on chapter 6 last semester. So basically it involves a die-in, okay, die-in like this, and a dienophile, okay. This is the simplest form or simplest example of dienophile, okay. In fact, this dienophile can have any substituents, okay. It can be like this. Since this is carbon, carbon can contain 4 bonds, so you can have any substituents over here, okay. R, this one also R, this one also R, okay, regardless any substituents. And these substituents will stay, okay. It doesn't being removed or anything, okay. What happens is just this die-in and dienophile will fuse together to form a cyclic, okay. What happened to these substituents? It will remain where? Here, okay. These two R will be positioned at this, the same carbon lah, since it is not being removed or anything, okay, or substituted even. So example, here you have an example of die-in, okay. This is originally the die-in, but the die-in itself is actually in a cyclic form. But remember, when you are dealing with Diels-Alder reaction, always focus on the die-in and the dienophile, which is this one. And what you have to know is this carbon over here, this carbon over here must form a new bond with this carbon, okay, this carbon, and as well as this carbon. It must form a new bond with this carbon. The rest, the substituents, will stay. It will remain. And the product forms will be something like this. Okay, it looks complicated, but actually it is not. So what happened is, this is the new ring. This one, the one below is the new ring. The one on top like this, okay, and this one is basically originally come from here, okay. But to draw it, it takes a little bit of what you call that, imagination lah, okay. So this is how a bicyclo ring being drawn, okay, on 2D paper, okay. How to show that the structures contain 2 rings on the same compound, okay. One will be what you call that, flat on the x-axis, and the other one will be shown like this, y-axis. Okay, stereochemistry of the Diels-Alder reaction. It is stereospecific. So the reaction, if the reaction is in syn addition, configuration of the dienophile is retained in the product. So let's see. Okay, let's say this is your die-in. Hello. And this is your dienophile. So once you add this carbon, take the pen, this carbon, okay, will form a bond with this carbon. Okay, same like this one will form a bond with this carbon. So once it form a bond like this, okay, there's a pointer. Okay, once it forms a bond, whatever what you call that, substituents will be at the same side. So if these two hydrogen, we start from hydrogen, is on the left side, then it should be on the same side. So once it is drawn like this in a cyclic, it cannot be right or left. So once in the cyclic form, if you still remember, you play with the models, okay, it is either in axial or equatorial position, okay, either pointing up or pointing down to the side. So this hydrogen must be pointing toward the same direction. So if it's on the right, it points upward. And these two carbonyl, C double bond O OCH3 or esters, okay, it is pointing towards away from this carbon, still on the same side. So this is syn. So the configuration of the diene is also retained on the product. So this is diene. So let's say now the diene also contain substituents. So this is simple diene, but now you have CH, CH, and then CH and CH. So let's say, oh sorry, CH3, CH3CH, CH3CH. So what happened is, if you look at the product form, at this carbon, okay, this is the same carbon, now already form a new bond with this carbon. So the hydrogen will be pointing towards the same direction. If you want it to show away from the carbon, then both of it must be away from the carbon. If it's this CH3 also is on pointing toward the same direction. Okay, so this is syn addition. So the diene reacts in the S-cis rather than S-trans conformation. So that means, okay, here you have a diene. The diene must be in this S-cis conformation. So the shape must be like this. Okay, it cannot be trans. Trans meaning one to the one pointing up, one pointing down. So if it's like this, the product form will be highly strained. So it is not actually to form this product very hard to form. So it probably requires a lot of energy, but in fact it is not really that stable. So it will revert back to the S-cis conformation. Okay, so the diene must be in this form, not on this type. Then occurs primarily in an endo. Okay, this is in regards if it have two what you call that ring. Okay, occurs primarily in endo, meaning away from the bridge, or rather than exo, which is towards the bridge. So what does it mean is, here you have exo. Exo meaning that away from the bridge. This is the bridge. Okay, away. Endo towards the bridge. Sorry, away. Sorry, endo is away from the bridge. Exo is towards the bridge. So what normally happen is it prefers this side. Okay, endo. Or if it's drawn like this, endo is pointing downwards. Sama lah macam ni, which is the same, which is pointing downwards. Exo is upwards and equatorial, okay, to the side. And identify the diene and dienophile necessary to synthesize phonic compound. So this is a question for you. So what kind of starting material that you can use to form this product? And also another one, these two. Okay, so these are another question for you. So that is all on what do you call that? Sorry. On today's lecture.